Bismillahirrahmanirrahim. Assalamu alaikum. In our today's video, we will discuss about Routh Hurwitz Criterion. In the previous video, we discussed that if the system order is higher than 2, it is difficult to find the stability or exact location of the poles. Routh Hurwitz Criterion is a method that yields stability information without the need to solve for the closed loop system poles. So it is very effective if we want to find the poles for a system that, which order is higher than 2. The method requires two steps. The first is to generate a data table that is called a route table, and the second method is to interpret that table to tell how many system poles are in left half plane, in the right half plane, and on the j omega axis. So let's discuss that how to generate the route table. For generating route table, we need the characteristic equation. This characteristic equation or polynomial is obtained by finding the equivalent transfer function, and this equation is the denominator of the transfer function. By taking the denominator, we first make two rows starting from the highest power of s, that is s raised power n, and next power s raised power n minus 1. Then we will write coefficient of s raised power n in the first place, the next an minus 1, then next an minus 2 will be written here, an minus 3, and like this pattern, an minus 4, and then next. So if any term is missing, we will write 0 for that coefficient. For example, if here s raised power n minus 2 consider it is missing, we will write 0 instead of a sub n minus 2. So this is our first step, is to make two rows of coefficients of this polynomial. The next step will be to make the third row. The third row will be s raised power n minus 2, one power less than this value. First value b1. b1 is obtained by dividing the next higher value, first value of the above row an minus 1. The common thing between b1, b2 and b3 up to so on, all this row, that minus 1 over n minus 1, this term will be divided with all these values like this, and the determinant, the first column of the determinant will also be same in all these values, an and an minus 1. For b1 we'll take next these two values, an minus 2, a sub n minus 3, like this. This will be our first value of first determinant b1, like this. For b2 we will take these two columns. This first column will be same in all these values, and the an sub n minus 1 will also be divided with all these values. For b2 we will write next two values in the second column. For b3 we will use first column and the next to b3, like these two values. Similarly, in this pattern we will complete all these rows. For c1 we will divide with minus 1 over b1. For c1 we will divide with minus 1 over b1, and these four values will be used in the determinant. For c2 we will divide again with -1 over b1. First column will be same, and next to this c. For c2, we will use first column as it is in the determinant and this value. For c2, first column will be this one and the second column will be this one. This is first column and this will be the second column, and -1 over b1 will be same for all these. For c3, this will be the first column and this will be the second column. So let's take another general example. Starting from the highest power, s raised power 4, and next x raised power 3, we have written the coefficients a sub 4, next a3, a2, a1 to so on a0. Any value is missing, we will write 0 there. S2 will be obtained. Above value -1 over 3 will be used in all this row. -1 over a3, minus again 1 over a3 here, and determinant will be a4, a3, a2, a1, a4, a3, a2, and a1. Similarly, for this value, first column will be same. For the second column, we will use a0 and 0. First column will be a4, a3. In this similar pattern, we will complete these values like this. Let's suppose this value b1. So here we will divide with -1 over b1 all these values. If this is c1, we will divide with -1 over c1 with all these values. And the first column will be same. For this term, first column will be a3 b1, a3 b1 in all these. For this d1, first column will be b1 c1 like this. So let's take this example with values. This is a third order system. First of all, we need to solve the feedback system because we need determinant of the transfer function. Our first step will be apply the feedback formula to get the equivalent closed loop system, and we will take the denominator of this system. Find the equivalent closed loop system because we want to test the denominator of the closed loop transfer function. Now our first step is to make the Routh table. So let's make a Routh table and label the rows with power of s from s3 to s0 in a vertical column. So here we will have 4 rows. Starting from s3 up to s0, we have placed the power of s. First 2 rows are obtained from the coefficients 1, 10, 31, and then 1013. Because this row can be divided by 10, we have simplified it by dividing with 10 to obtain a smaller value. For getting this first term, we will divide with -1 with all this row. 1 and 1 will be used here in first column, and 31 and 103 will be used here. Okay, so taking this minus of the formula and 1 from here, first column is obtained from here, and this will be used in all these first column. And 31 103 will be used from here, it will be written here. 00 will be the second column of this. If any column of the determinant is 0, we know that the answer will be equal to 0. So we will not solve this term. So next, minus 72 will be divided here, minus from the formula, and for this s raised to power 0, the second column of the first column of the determinant will be obtained from here 1 and minus 72. It will be used in all these such values, and the second column is obtained from here. This is the first column and this will be the second column. By solving these values, we get 1 1 minus 72 and 103 in this column. We have formed the first and second row using the coefficient of this polynomial of the denominator. So here we have written after getting these values in a simplified variant to exactly know the values. So now we will discuss three cases. Two cases will be discussed in this video, and one case will be discussed in the next video. Case 1 is when no zero element in the first column of the Routh table. These three cases are used for the interpretation of the Routh table. Our first step is to make the Routh table starting from s cube, s square, s1 and s naught, 1 and then 1 coefficient, 2 and 8. Minus 6 is obtained by dividing minus 1 over 1 and taking the term 8 minus 2, which is equal to 6. This will be the first column and this will be the second column of the determinant, like this, minus 1 over 6. So this minus 6 was obtained from here, and 8 is obtained by dividing this minus 1 over minus 6, 1 minus 6 and 8 0. So plus 48 will be divided with 6 will be equal to 8. So for the interpretation of the Routh table, we need only the first column. The number of sign changes in the first column will be equal to the unstable pole or the poles in the right half plane. In this example, we have two sign changes. Like here we have positive sign, here we have positive sign, no sign change. From here positive to negative, this is first sign change, and then again negative to positive, this is second sign change. So we have two sign changes. That means we have two poles in the right half plane. So this system is unstable. Number of sign changes in the first column is equal to the number of unstable poles. Let's take another example. We have solved our Routh table by the method as discussed earlier. We just solve this first column. To elaborate, this value will be obtained like this: minus 1 over 3, the value above from this term, and coefficient will be obtained, and this 2, 3 and 5, 2 will be, this will be equal to 4 minus 15, so will be equal to minus 11. The answer will be plus 11 over 3. Similarly, this value comes to be minus 32 over 11 and plus 6. So how many poles will be in the right half plane? This will be equal to number of sign changes in the first column. How many sign changes in this first column? This will be our first column. From positive to positive, there is no sign change. Again, no sign change. Here we have first sign change. From positive to negative, one sign change, and from negative to positive, this is second sign change. So there are two sign changes. That means we have two poles in the right half plane. Two sign changes, positive to negative and again negative to positive. So two unstable poles. Number of sign changes in the first column is equal to the number of unstable poles. The remaining poles will be in the left half plane. For imaginary axis, we will see the case number 3. So interpreting the basic Routh table. The basic Routh table applies to the system with poles in the left and right half planes. The Routh Hurwitz criterion declares that the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column of the Routh table. Like this example, how many sign changes in this Routh table? Two sign changes. That means we will have two poles in our right half plane of the S plane. In this pole, right half plane, that means the system will be unstable. So let us discuss the case 2. Zero element in the first column. First of all, we will make two rows. S maximum power s raised power 5 and s raised power 4. Write coefficients 1, 2, then 2, from here 4, 11 and then 10. B1 will be equal to minus 1 over 2, 1, determinant of 1, 2, 2, 4 and 4 minus 4 will be equal to 0. So B1 is equal to 0. If we continue with this calculation, we came to know that if the first element is 0, we have to divide all this next row with minus 1 over 0. So all this row will be equal to infinity. So we cannot proceed with this term 0. So we will assume that 0, we replace with this 0 with epsilon. That will be a very small value. So let's discuss this. C1 will be equal to minus 1 over 0. Forget these values because the answer will be infinity. So we take B1 is equal to epsilon, that is very small value, that is approaching to 0. that is approximately equal to 0. So C1 will be now C1 will be a value that is that will have epsilon in its calculation, its value. We will proceed in the same way. Like here we have minus, instead of 0 we will write epsilon here. Here we will have minus 1 over 2 10 minus 22 like this. So 10 minus 22 will be equal to minus 12, so positive 6. So here we will have 6, and here we have minus 1 over epsilon, 2 epsilon, and 4 and 6. So solving this value 12 minus 4 epsilon, so okay, when we will multiply this term minus 12 over epsilon plus 4 epsilon, here we have 4 plus 4 epsilon. Why we have not written this 4 epsilon? 4, only 4, because epsilon will be cancelled out. Because one something over 0 or something over very small value will give us very large value as compared to the 4. So this 4 will be negligible. We have write only this minus 12 over epsilon here. So our first step is to, if we have first element of a row is equal to 0, we will replace this 0 by a small number epsilon, and we'll solve with the help of epsilon, and we will then continue the array, and now we'll get S1 and S0. So we not confirm that whether epsilon is positive or negative. So let's take epsilon positive. So if we have positive, then here we will have a negative value. Looking at this first column of this Routh table, we came to know that there are two sign changes. Now let's take the value of epsilon negative. Here we get the positive value. Again, from positive to negative and negative to positive, we have two sign changes. So whether we take epsilon positive or negative, we will have two sign changes. That means two unstable poles. So this is an unstable system. Two sign changes, whether epsilon is assumed positive or negative. So two roots in the right half plane. That means unstable system. For another case, first element of a row is 0. We will replace this row with epsilon, and so this is our previous example. This is another example, but it has same 12 or minus 12 or epsilon. So but this is again having two sign changes. So this is again unstable. So two poles in the right half plane. So taking another example, s raised to power 5, coefficient 1, again 1, 2 from here, 3 will be written from here, 1 and 4. And this one will be from here. This s raised power 3 is obtained by dividing minus 1 over 1. First column 1 1 and second 2 3. this is equal to 3 minus 2, so minus 1 due to this minus. As we get 0 in this value, we have replaced with 0 with epsilon. We will continue our calculation with this epsilon until we get this first column. Let's assume that epsilon is positive. We will get positive value, again we get positive value. So in this we get two sign changes. Now let's take epsilon negative. So here we will get negative value and here we will get again negative value. So positive to negative, one sign change, no sign change, again no sign change, and then second sign change will be from here. So in this example we will again have two sign changes. So whether assume epsilon positive or negative. So we have two poles in the right half plane, the remaining poles will be in the left half plane. Let's complete our discussion of first two cases. Let's recap. In this video we have discussed about the Routh Hurwitz criterion. We have make Routh table and interpret it to get the how many poles in the right half plane or in the left half plane. In this next video we will discuss the third case, if any complete row is 0, how to solve this. So we will meet in the next video. Till then, Allah Hafiz.